in phase diagrams, locating phase boundaries, liquid vapor equilibrium, liquid equilibrium, and solid liquid equilibrium. So marami tayong discuss guys, okay? So topic lang tayo, okay? Again, ano sabi ko? Pace yourselves guys, okay? Huwag masyadong ma-overwhelm, okay? As long as huwag niyong tampakan ang sarili niyo. G guys, G, okay? So medyo pause lang ako guys, so please bear with me. Okay? But I'm still here with you, okay? Now, let's look at the phase boundaries of water. So here guys, we have phase diagram of water. Okay? Now, as temperature increases guys, here at your x-axis, the vapor pressure, it also increases. Nangyayari. It is because more molecules, they have enough energy to escape from the liquid phase and into the vapor phase. But here guys, if you increase the temperature, and then vapor pressure also increases. Nangyayari yan again. And kung nangyayari yan again, water vapor is formed from the water or liquid phase. Okay? And this continues until the critical point, diba? Here. And beyond the critical point, guys, the liquid and vapor phases, they become indistinguishable. Okay? Now, the lines separating the two phases, such as ice and water and water vapor, they are called the phase boundaries. Okay? And they indicate that they are in equilibrium since their chemical potentials are equal. So we can say, guys, that the chemical potential of ice is in equilibrium or equal with the chemical potential of water. That's why in this phase boundary, they are in equilibrium. And then for between water and water vapor, okay? Because their chemical potentials are equal. Or their tendency to change or their tendency to react, okay, is also equal. Okay? Now, these are the various parts of the phase diagram. So first we have the melting or freezing curve. Okay, so ito yun. Now, in this curve, it has a negative slope, right? Negative slope, which indicates that ice, it is less dense than water. What does this imply? It implies that increasing the pressure, okay, so for example, if you increase pressure, then it melts ice more easily. Again, if you increase the pressure, it melts ice more easily. Therefore, you would need a lower melting point in order to melt ice into water, okay, as you increase the vapor pressure. Next, we have the boiling or condensation curve, ito yun, okay? And it indicates that the pressure, it increases with the boiling point, okay? So what does this mean? The increasing pressure, okay, makes it more difficult to vaporize water. That's why you would need a higher boiling point in order to vaporize water or convert water into water vapor. Next, we have triple point here. So here, all three phases coexist at equilibrium. So, ang value ng triple point nyo is at 0.01 degrees Celsius and 611.66 PA. Okay? Now, the critical point here, it is the endpoint of the liquid gas curve or the condensation evaporation curve. Okay? And ang value nito ay 374 degrees Celsius and 222.1 megapascal for water. Okay? So, beyond the critical point, a supercritical fluid forms, okay, SCF. And here, in your supercritical fluid, your liquid and gas phases become indistinguishable. Okay? Hope it's clear, guys. Now, how do we determine which of the following intensive variables such as temperature and pressure can we vary in a phase diagram? So that is through the Gibbs phase rule. Okay? So again, the Gibbs phase rule provides a number of intensive variables such as pressure and temperature that can independently change while the number of phases is retained in equilibrium. Okay? And this gives us the degrees of freedom F. Okay? So degrees of freedom F is equal to C minus P plus 2, where C is equal to the number of independent components, P is equal to the number of phases in equilibrium, and S is the number of actual chemical species. Okay? So guys, if there is no chemical reaction, then we can say that C is equal to S, meaning the number of independent components is just equal to the number of actual chemical species. However, if we have a chemical reaction, then C is less than S, okay? Where C, okay, is equal to S minus 1. Okay? So that's how we can determine the degrees of freedom. Next. Here we have a phase diagram, okay? Now, within one phase, so for example, dito kay phase alpha, we have one phase. So how can we determine the degrees of freedom? So F is equal to component. So here in this case, we have one component minus 1 because we have one phase present in this region plus 2. Diba? The degrees of freedom is equal to 2, meaning two intensive variables can be varied, which is both temperature and pressure. And what do we call these types of systems? They are bivariant. F is equal to 2. Next, guys, let's go at the boundary lines, okay? So at this point, you will have two phases. So F is equal to 1 minus 2 plus 2. Yan. F is equals to 1. When F is equals to 1, one intensive variable can be varied at the equilibrium line. So ganun din. F is equal to 1 at the equilibrium lines dito. And they are uniform. And lastly, how can we get F is equal to 0? So mahanap natin yan sa mga triple points, diba? So water may mga triple points tayo. Okay, so it's F is equals to 0, right? O tingnan nyo pa. F is equal to 1 component for water, minus 3 phases for triple point plus 2. O guys, ilan yan? 0, diba? What does this mean? Then, the intensive variables such as the temperature and pressure are fixed. Okay? I hope it's clear, guys. Let's proceed. Now, let's determine the number of degrees of freedom for the phase diagram of water. So, within the phases such as the water, ice, and water vapor, okay, we can calculate the degrees of freedom through F is equal to C minus P plus 2. So, we have one component, right? It is just water. So, 1 minus 1, we have one phase in the water region, plus 2. So, we have F is equal to 2 at the phases here, meaning we can vary both the temperature and pressure in these regions. However, at the equilibrium lines, okay, F will be equal to 1 minus 2 plus 2. So, F is equal to 1. Therefore, at the equilibrium lines, you can only vary one variable. So, for example, you vary the temperature at this equilibrium line. O, dito yung temperature nilagay mo dito. Dapat yung temperature niya ay ito. Okay? So, the pressure will follow. Okay? It corresponds to a pressure at this point. Okay? Ganon yun. Next, okay? At the triple point, again, F is equal to 0, meaning its variables are already fixed. Okay? At a certain temperature and pressure. Okay? Now, let's try to find the degrees of freedom for each of the following examples. First, we have superheated steam. Oh, guys, ano kaya yan? So, here, our C or S in this case, since we don't have a reaction, since we don't have a reaction, okay, is water, right? It is our only component, and our phase is only one, which is the vapor phase for superheated steam. So, steam. So, solving for the degrees of freedom F, we get C minus P plus 2 is equal to 1 minus 1 plus 2 is equal to. Therefore, we can vary two variables for superheated steam. Next, we have methanol water mixture. So, guys, in this case, you have two components or actual chemical species, or C. Okay? That is methanol and water. Therefore, C is equal to 2. And the phase is just 1 because here you have, guys, a completely mixed liquid, right? Because methanol and water are soluble with each other. Solving for the degrees of freedom, we get 2 minus 1 plus 2. That is equal to 3. Okay? I hope it's clear, guys. When we say we have a degrees of freedom 3, we can vary the temperature, pressure, and composition, or number of moles for the methanol water mixture. Okay? Again, next, find degrees of freedom for each of the following. So here we have a reaction. Okay? Let's analyze, guys. The actual chemical species S that we have, there are copper oxide, ammonia, copper, solid, water, and N2. These are all 5 in total. Okay? 5 in total. Now, for the phases, guys, we have 3. First is copper oxide in solid form, copper in solid form, and gas. So, guys, take note of copper oxide and copper. Okay? They are in different solid phases. So, we have 3 total phases. Solving for degrees of freedom. Okay? First, we have to get C is equal to S minus 1 because we have a reaction here. So S minus 1, 5 minus 1, that is equal to 4. Therefore, your C is equal to 4. Solving for the degrees of freedom, we get 4 minus 3 phases plus 2, and that is equal to 3. Okay? Meaning in this reaction, you can vary the temperature, pressure, and composition. Okay? Now, how do we precisely locate a phase boundary in our phase diagrams? Now, this is described by the Clapeyron equation. Clapeyron equation, okay, as shown here. Now, at equilibrium, guys, take note that the chemical potentials of phase alpha and phase beta are equal, right? Diba pinakita ko yung ganyan? Kasi they have the same tendency to change, or they have the same tendency to react, okay? So, given that fact, guys, we derive the Clapeyron equation through this expression, okay? Where the chemical potential of the alpha phase is just equal to the chemical potential of the beta phase, okay? Now, we know, guys, that the d mu, the change in the chemical potential, is equal to negative S bar dt plus V bar dt, right? So, let's just simply substitute that. So, we have negative S dt plus V dp in terms of alpha for alpha phase, and that is equal to negative S dt plus V dp for the beta phase. So, let's just rearrange the equation where we have dp on the left side, all dp's on the left side, and dt on the right side. So, rearranging, we get V alpha minus V beta dt is equal to S alpha entropy minus S beta dt. Now, with this, guys, with continuing rearrangement lang, diba? dp over dt is just equal to the change in S divided by the change in V, right? Ito na yun. This is your Clapeyron equation. Okay? Diba? Carry lang. So, ma'am, what does this mean? Bakit dinidescribe niya yung slope ng isang phase boundary? So, guys, tingnan nyo to. Okay? This expression here shows us that pressure changes with temperature, and it depends on how much entropy and volume changes during the phase change. Okay? So, if you have a larger entropy change, okay, then there is more disorder. Therefore, it would have a bigger impact on your slope. Meanwhile, if you have a big volume change, then you need more space, right? You need more space. That leads to a steeper slope. Okay? For example, guys, gusto natin mag-boil ng water. Okay? From liquid to gas, diba? We know that there is a big increase in entropy and also a big increase in volume. Right? Increase. Okay? So, what can we say about this slope? If we have a boiling water, it is positive. Okay? It is positive because of the increase in delta S and the increase in delta V. Okay? Increase. But guys, not infinite. Okay? Now, another form of the Clapeyron equation is this. So, dp over dt. So, the change in pressure with pressure is equal to the how much heat is absorbed or released during a phase change divided by temperature and volume change. Okay? Again, delta H, it is the heat needed to melt, boil, etc. T. Okay? If we have a higher temperature, guys, ano kayang mangyayari? Then there would be a less dramatic pressure change because if this gets bigger, then this expression gets smaller, right? Kasi palaki na palaki ang denominator mo. So what will happen to dp over dt? So you will have a less dramatic pressure change for dt. Okay? So for example, let me have boiling water. Okay? Again, delta H, it is the heat we need to vaporize the water. And this is your latent heat. Latent heat, right? So delta V bar naman to. Okay? It explains how much a substance expands or contracts, diba? So it will show us a volume change from liquid to gas. Okay? So it tells you how much pressure must change with temperature to keep the water boiling. Okay? I hope it's clear, guys. Let's proceed. Yeah. Now, we also have what we call the cautious Clapeyron equation, and it is derived from the Clapeyron equation, and it estimates how vapor pressure, okay, is related with temperature during a phase transition. So this is the equations. Okay? So for the first equation, it describes how vapor pressure changes with temperature. Okay? So if you know the vapor pressure of one temperature, let's say T1, you can predict the vapor pressure at another temperature T2 using the heat of vaporization, itong delta H nito. Okay? Now, itong right equation naman, it is the simplified version of the cautious Clapeyron equation, and it is used to plot a graph. So if you plot L and P, your Y, versus 1 over T, your X, okay, then it will give you the slope of the line. Okay? So it is negative delta H over R. So from this slope, guys, we can just determine the enthalpy. Okay? Enthalpy. I hope it's clear, guys. Okay? So in other words, guys, if you plot vapor pressure against temperature the right way, then the slope of the line negative delta H over R will tell us how much heat will it take to boil the liquid, or in other words, the enthalpy. Okay? Hope it's clear. With that, let's try this to solve this sample problem. Calculate the enthalpy of vaporization in kilojoules per mole given the following set of data. So here we are given the set of data. So our X again is 1 over T, and our Y is Ln P. So we get 1 over T, that is 1 over 7 plus 273 Kelvin, and so on and so forth. Okay? Meanwhile, Ln P, it is just simply Ln 32.42 torr, and so on and so forth. Okay? So, bakit guys, niretain natin si torr? That is because, okay, the units torr, they cancel out in the pressure ratio, P2 over Q, okay? So later on, you will see that. Now guys, input nyo lang to sa calculators nyo, ano kaya makuha natin na value? And guess. So we can get the enthalpy of reaction that is equal to 35.7 kilojoules per mole, okay? So note guys that, syempre, hindi ito yung value nito, okay? So to get this value, for example, may value ka na ng slope, let's say it's M, their slope, it is equal to negative delta H over R, right? So to get delta H, you would have to multiply the value of the slope to the universal gas constant, dito, times negative 1, and then you get the enthalpy, okay? Which is equal to 35.7 kilojoules per mole. I hope it's clear, guys. Let's proceed. For many substances near the melting point of the solid, the density of the liquid is less than the density of solid. What is the effect on the melting point when the system is doubled? So guys, okay, this is the phase diagram of most substances, okay? So water, baliktad. Di ba si water positive yung slope between the solid and liquid? Now guys, for most substances, okay, we have a positive slope, okay, between the solid phase and the liquid phase, okay? And this means that the density of the liquid is less than the density of the solid. So what happens with the melting point? No. Ang meaning ito guys, when we increase the pressure, as we increase the pressure, the solid phase is more favored, okay? So in order to transform the solid phase into the liquid phase, then we have to increase the temperature, we have to increase the melting point in order to transform solid into liquid, okay? That is what it means by solid is denser than liquid, okay? So we have to, again, increase the melting point. Now, for water, again, it is the opposite, okay? We know that water is denser than ice, right? So if you increase the pressure, then that means the formation of the liquid is favored. Therefore, guys, as you increase the pressure, then the melting point decreases, or it will take you a lesser amount of temperature, lower amount of temperature in order to melt the ice into water, okay? Take note of this difference, guys, okay? Important na, that's yung concept na ito. Now, let's move on to the next part of our crash course. It is the liquid vapor equilibrium. So to further understand what liquid vapor equilibrium is, kindly watch this video, please.
Let's use our example of a liquid mixture of water and ethanol. If we place a bowl of the mixture inside a closed container, molecules of both water and ethanol will enter the vapor because of the vapor pressure of each component. At equilibrium, how much of each component will be in the vapor mixture? The answer depends on the relative vapor pressure. Since the vapor pressure of ethanol is higher than water, ethanol is more volatile than the water. Therefore, ethanol molecules will want to escape from the liquid in a higher ratio than water. At equilibrium, the concentration of ethanol in the vapor will be higher than the concentration of ethanol in the liquid mixture. Since the vapor has a higher concentration of ethanol, the liquid must have a lower concentration than before any of the ethanol evaporated. As a result, the liquid has become less concentrated in ethanol.
So guys, gets na ba? Ganun ang ating liquid vapor equilibrium. So for example, again, if ethanol, which is more volatile than liquid, okay, if it goes from the liquid phase to the vapor phase, edi mas tataas ang concentration ng ethanol in your vapor phase and then bababa ang concentration ng ethanol in your liquid phase. Okay? So that is what a liquid vapor equilibrium talks about. Okay? So to define a liquid vapor equilibrium, okay, basically guys, the same number of liquid molecules are evaporating as vapor molecules are condensing. Now, the amounts of liquid and the amounts of vapor, they stay the same as molecules keep moving between the liquid phase and the gas phase. Okay? So guys, if you basically plot vapor pressure against temperature the right way, okay, we can determine the liquid vapor equilibrium. Okay? Now guys, we can actually differentiate the types of liquid vapor equilibria in solutions. Okay, so we can have an ideal solution or a non-ideal solution. Now guys, the type of liquid vapor solution that we have depends on the volatility or the non-volatility of the solute that we have in our liquid vapor solution. So guys, to know that, kindly watch this video first.
Hi, I'm Robin Higgins, and this is volatile versus non-volatile in chemistry. All right, so volatility is the measure of a substance's desire and ability to become vapor, otherwise gas. So if you take an example of having a flask full of water, this is all liquid water, but it doesn't stay that way. We know that if we leave a cup of water just out, it'll eventually evaporate, and that's because of the process of this liquid water and its molecules slowly becoming vapor. So with every liquid, there's a natural equilibrium of the liquid molecules wanting to escape out, and they burst out of the surface, and then they become a gas. And this is just because enough of them will have various energies that will be able to get them out, and of entropy, and them moving so fastly in so many directions that just eventually some of them become gas. And so this is how we have vapor pressure. Liquid molecules becoming gas molecules. And volatility is basically how much does this happen. So with water, it happens. You have a cup of water, it's going to take a while for it to evaporate. And every liquid has its own volatility. So ethanol, let's look down here, is the stuff that all alcohol is made of, is actually much more volatile than water. So if you have them, and these are both enclosed flasks, just because scientists need to observe what's happening, we can't just let our ethanol or water escape into the environment. So many, many, many more ethanol particles will become gas or vapor than water. And this is because the intermolecular forces that keep ethanol bonded together are a lot weaker than the intermolecular forces that keep water bonded together. So ethanol is like, I don't really care if I'm next to everyone that's like me, I'm just going to escape into the gas. And because of this, there's more gas particles, and so the vapor pressure increases. So we would describe ethanol as volatile and water as non-volatile. And there's no real hard cutoff, it's just kind of a comparison thing. Which one does it more than the other? So another example of something that's very volatile is frozen dry ice, or frozen carbon dioxide. And that actually goes from being a complete solid to a gas. It sublimates, and that's extremely volatile. It happens very quickly. All of those solid particles want to escape and become gas particles. I'm Robin Higgins, and this has been volatile versus non.
Ayun guys ha, so now you know the difference between a non-volatile and a volatile liquid, okay? So that will help you in our next discussion, okay? So here guys, we have here, in this situation, we have a volatile solvent A plus non-volatile solute B, okay? And then what happens in their liquid vapor solution, okay? So if you mix a non-volatile solute B to a volatile solvent A, okay, the vapor pressure of the solvent will decrease because of the presence of the non-volatile solute, okay? So ano nangyayari guys dito sa figure na to? The non-volatile solute B, okay, hindi siya mag-evaporate kasi non-volatile siya. So i-dilute niya lang si volatile solvent A. That means fewer amount of molecules, of A molecules, will escape into the vapor phase. And that contributes to its lower vapor pressure. Again, kasi nadidilute ni non-volatile solute BCA, okay, then fewer molecules of A will escape into the vapor phase, and that leads to a lower vapor pressure. Okay? So guys, this is quantified by the equation based on the Raoult's law. PA is equal to XA times P naught A, or PA is the vapor pressure of the solution, which is lowered. That is equal to the mole fraction of the component A times the vapor push pressure of solvent. Okay? Ayan. Now another type is when we have a volatile solvent A plus volatile solute B. Now what happens? Now both A and B, they can evaporate, right? So each will contribute to its own, so each guys, they will each contribute a partial pressure to the gas above the solution. So imagine you guys, meron kayong benzene and toluene, okay? They can both evaporate. Now, their individual vapor pressures, they will add up to create the total vapor pressure above the liquid. Again, they will add up to create the total vapor pressure above the liquid. Okay? It makes sense, right? Because you have two species that will evaporate. Okay? And of course, guys, if you have two volatile liquids, okay, that means they will contribute separate partial pressure. So how do we calculate for the total vapor pressure? That is through the Dalton's law. So the total pressure is equal to the partial pressure of volatile solvent A plus the partial pressure of the volatile solute B. Okay? And we can solve PA and PB based on Raoult's law and Dalton's law. Okay? So when we say, guys, PA is equal to XA times P naught A, that is also equal to the mole fraction of the component A in vapor times the total vapor pressure. Okay, dapat tandaan ko guys para madaling relate. Okay, then for the partial pressure B, that is equal to XB P naught B. Okay, this is based on Raoult's law, and that is equal to the mole fraction of component B in vapor phase times the total vapor pressure. Okay, again guys, very important ang mga equations na ito. Now with that, let's try to answer this one. Okay, at 90 degrees Celsius, the vapor pressure of 1,2-dimethylbenzene is 20 kilopascals, and that of 1,3-dimethylbenzene is 18 kilopascals. What are the compositions of the liquid and vapor mixtures that boils at 90 degrees Celsius when external pressure is 19 kPa? Okay, so we are given again the vapor pressure of solvent A. Okay, of component A, and that is 1,2-dimethylbenzene. Then we're also given the vapor pressure of 1,3-dimethylbenzene. And then their total vapor pressure is 19 kilopascals. So kailangan natin hanapin ang compositions ng liquid and vapor phase. Okay? So first guys, let's use this. Okay? So the total pressure is equal to the vapor pressure of component A in solution plus the vapor pressure in component B in solution. So guys, iba to sa P naught A and P naught B, right? Because these are the vapor pressures of pure 1,2-dimethylbenzene and pure 1,3-dimethylbenzene. Okay? So let's solve for the vapor pressures of A, 1,2-dimethylbenzene in solution, and the vapor pressure of B, 1,3-dimethylbenzene in solution. Okay? Through the Dalton's law. So how can we do that? Ayan lang guys. So substitute lang natin yung ating equation for the Raoult's law for finding the vapor pressure of A and B in solution. Okay? So PA is just equal to XA times P naught A, and PB is just equal to XB times P naught P. Okay? Now, we know, guys, the value of P naught A, we know the value of P naught B, and we know the value of PP. So we can solve for XA, the mole fraction of A, or 1,2-dimethylbenzene in liquid phase, and the mole fraction of component B, 1,3-dimethylbenzene in liquid phase. So solving 19 kPa, that is equal to XA times 20 kPa, ito, P naught A, plus 1 minus XA. So guys, tandaan nyo lang, diba? You have two components in your mixture, si A and B. A and B. So, the mole fraction of A in the liquid phase plus the mole fraction of B in the liquid phase is just equal to 1, right? Kasi mole fraction yung tawag, diba? So, for example lang meron kang 1/2 of component A in your liquid phase plus 1/2 of component B in your liquid phase. And that is equal to what? 100% of the mixture. Okay? Dapat gets yun, guys. So, ano si XB? If this is the case, then XB is just equal to 1 minus XA. Kaya nilagay natin dito, 1 minus XA times 18 kPa. So simply guys, just input this in your calculator. Ito yung sinasabi ko guys, kailangan magaling na tayo mag-shift solve. Okay? Kasi mas madali. Kasi na, ito-transpose pa natin lahat ng mga variables. Okay? It is very prone to error. So guys, shift solve and you will get the value of XA, or the mole fraction of a component A, 1,2-dimethylbenzene in liquid phase, and that is equal to 0.5. And for XB, the mole fraction of B, or 1,3-dimethylbenzene in liquid phase, is 1 minus 0.5 equal to 0.5. So now we have the compositions of 1,2-dimethylbenzene and 1,3-dimethylbenzene in liquid phase. Now, kailangan natin mahanap guys ang compositions nila in vapor phase. Okay? So this is through these equations guys. Diba? Kaya natin ma-relate sila. So simply guys, the mole fraction of A, 1,2-dimethylbenzene in the vapor phase is just equal to XA P naught A divided by PP, right? Based on this equation. Substituting, because we all know these values, alam may value na tayo for XA, we get 0.5 times 20 kilopascals divided by 19 kilopascals. And we get YA, the mole fraction of A, or 1,2-dimethylbenzene, is equal to 0.526 or 52.6% in the vapor phase. So paano natin makukuha ang mole fraction ni component B, or 1,3-dimethylbenzene in the vapor phase? Guys, simply, again, the mole fraction of A in the vapor phase plus the mole fraction of B in the vapor phase is just equal to 1. So YB is simply equal to 1 minus YA. So 1 minus 0.526, that is equal to 0.474. So the mole fraction of component B, 1,3-dimethylbenzene, is 0.474 or 47.4% in the vapor phase. Ayan. Clear ba guys? Ganun sumagot ha? Okay. Of course, meron sa board exam, okay? Now guys, this figure here shows a typical liquid vapor phase diagram. So in a typical liquid vapor phase diagram, we have two components, component A and component B. Okay? And we can measure the relative amounts of component A and component B in the liquid and vapor phases through this phase diagram. So imagine guys that the phase diagram, it represents a liquid in a cylinder. You need to write, okay? And the cylinder has a piston. So if you increase the pressure, okay, if you push the piston, it favors liquid formation. While decreasing the pressure, guys, and this is by pulling the piston, it favors vapor formation. Okay? Diba? Tama, diba? Lower pressure, it favors vapor formation, diba? Because the molecules are far apart. While increasing the pressure, diba? The molecules will be held closer together. That's why it favors the formation of a liquid. Okay? So here, guys, in this graph, we have here what we call the liquid phase and the vapor phase. In this region, okay, this is purely liquid. Okay? So your mixture of A and B here is purely in liquid phase. Tapos dito naman in this region, okay, the mixture of A and B here is purely in vapor phase. Okay? Now, we have what we call here the ZA. This is the overall composition of the mixture, or the total mixture composition. It tells us the overall percentage of component A in the whole system, and not just in one phase. Okay? So if we look at a mixture of two substances such as A and B, so ZA, if it is equal to 40%, meaning 40% of the mixture is component A, and 60% of the mixture is component B. Yun ang meaning ng ZA. Okay? Now guys, we have here what we call the isoplet. So this is a vertical line. Okay? So the vertical line, the isoplet, okay, it shows us how as we go down and change the temperature, okay, or change the pressure, okay, it tells you how much, it shows us how the system changes with temperature and with pressure, okay, as we keep the overall composition of the mixture constant. Again guys, the isoplet here, it shows us how the system changes, okay, as we change the pressure or the temperature, okay, while keeping the overall composition of the mixture constant. Okay. Now guys, we have what we call here the bubble point, okay, and the dew point. Now these points are situated in various curves. So first, the blue curve here is what we call the liquidus curve, okay, liquidus curve. And this here, the red one, is your vaporous curve. Okay? So the vaporous curve, it touches the vapor region. The liquidus curve, it touches the liquid region. So guys, at the bubble point, the first hint of bubble forms. Ang unang bula ay magfo-form. Oh guys, anong meaning pag may bulang nagfo-form? Anong meaning yan? Meron nagfo-form na vapor from liquid, right? Diba? Pag nagkukulo tayo ng tubig, diba? Ang unang nangyayari ay may nagfo-form na bubbles, diba? Parami ang bubbles. So the bubble point, it shows us the first hint of vapor. Now guys, between the bubble point and between the dew point, or between the liquidus and the vaporous curve, you have existing two phases. Again, you have two existing phases. Okay? So here, you have both liquid and solid, and they are coexisting. Okay? So, for example, guys, how can we determine the relative compositions of component A and component B within this region? Okay, so that is through our tie lines. Okay, guys, pag sinabi kong tie line, ito yun, it is a horizontal line connecting two points, which are the liquid and the vapor compositions. Okay, again, the tie line, it helps you connect the liquid and vapor compositions. So here, guys, basically, ang sinasabi lang dito, yung tie line represents the equilibrium between two phases. Okay, so meaning, guys, within the tie line, in equilibrium ang ating liquid phase and vapor phase. Okay, so it shows us how much of each phase is present at a certain temperature. So later, makikita natin yan. Now here we have the dew point. Now in the dew point, guys, the last drop of liquid forms. The last drop of liquid forms. So as we decrease the pressure, guys, diba? We pull the piston. Again, that favors vapor formation. So when we decrease the pressure and we have reached the dew point, okay, the last drop of liquid forms. And beyond the dew point, dito sa baba, okay, your mixture is now purely vapor. Okay, I hope that's clear, guys. If not, we have a good example for that. Okay. Now, guys, throughout the phase diagram, okay, we have varying mole fractions of component A and component B on the liquid phase and in the vapor phase. Diba? Throughout the phase diagram. Bakit? Diba? Down the isoplet, guys, ang ginagawa natin is we decrease the pressure or we increase the temperature as we go down the isoplet. Now guys, syempre, kung nag-increase yung pressure or nag-decrease yung pressure or nag-increase yung temperature, may effect ito sa relative amounts of component A and component B present in the liquid phase and your vapor phase. So, here are the steps in determining, okay, the relative amounts of A and B in the liquid and vapor phase. Again, guys, ang basis natin dito is the isoplet. Because as we go down the isoplet, we are decreasing the pressure, or in this case, Guys, again, we are decreasing the pressure, okay? Or either increasing the temperature, okay? Depende sa graph. So guys, tingnan natin. At point 1, observe that all we have here is liquid, right? At point 1. So meaning ito guys, the mole fraction of A, of component A at point 1, is just equal to the overall composition of the mixture. Okay? Now what about the mole fraction of component A in the vapor phase? Siyempre guys, that is equal to 0 because lahat ito ay liquid pa lang. Wala kang form na vapor dito. Okay? Then what about XB, or the mole fraction of component B? That is just equal to 1 minus XA1, right? XB1. So the mole fraction of component B at point 1 is just equal to 1 minus XA1. Okay? And for YB1, mole fraction of component B at point 1, that is also equal to 0. Next, let's decrease the pressure. Okay? Pupull natin yung piston. Okay? Until we reach point 2. Oh guys, anong meron sa point 2? Anong point na yan? Yes, that is your bubble point. Here, may unang bulakan nang nagpo-form. Here, boiling starts. Therefore, at this point guys, meron ka ng vapor na nagpo-form konti. Okay? So, the mole fraction of component A in the liquid phase at point 2 is just equal to, XA2 is equal to ZA. Bakit ZA guys? Dapat guys, pag tinitingnan natin kung ano ang mole fraction ng ating component at a certain point, okay, we must reflect it based on its liquidus curve or vaporous curve. So, for the mole fraction of A at the liquid phase, we have to reflect it on our liquidus curve. Tingnan nyo lang yung liquidus curve nyo guys. At point 2, andito siya, diba? And if you reflect that, ibig sabihin naman ito guys, the mole fraction of component A at point 2 is just equal to the overall composition of the mixture ZA. Okay? And then guys, here, we can now determine the mole fraction of component A at point 2 in the vapor phase. Paano natin gagawin yan? Again, we have to reflect it on our vaporous curve. So, mag-create tayo ng tie line dito sa gitna ng liquid mole fraction mo and vapor mole fraction mo. Okay? So, the mole fraction of component A at point 2 is just equal to, okay, ito na yun guys. Okay? Now, what about YB2? Okay? What about the mole fraction of component B? So, that is just 1 minus YA2. Okay? Whatever man ang value ni YA2 na yan. Now, guys, let's further decrease the pressure until we reach point 3. Now, at point 3, guys, notice that we are on the middle of your liquidus curve and vaporous curve. So, dito guys, mas marami na ang amount of vapor present compared to point 2. Again, dumadami na ang amount of vapor mo as we go to point 3, as we decrease the pressure. Okay? So, ano nangyayari guys? Meron na tayo mole fraction of component A at point 3 and mole fraction then of component A at point 3 in the vapor phase. Okay? So, first guys, the mole fraction of component A in the liquid phase is just equal to the mole fraction of component A in the liquid phase at point 3, whatever the value is here for XA3. Okay? Tapos, the mole fraction of component A in the vapor phase at point 3 is just equal to YA3. Okay? So, what about XB3? Again, it's just equal to 1 minus XA3. And for YB3, the mole fraction of component B at point 3, that is equal to 1 minus A3. 1 minus YA3. Y1 minus YA3. Now guys, in order for us to really determine the relative amounts of liquid and vapor, we have to create tie lines, okay, tie lines in between ZA and YA3. So ito, tie line, isang tie line. Okay, and another tie line. Again, this represents equilibrium between two phases. Okay? So guys, how can we exactly determine the relative amounts of liquid and vapor at point 3? That is through the inverse lever arm rule, or the lever rule in short. Okay? So guys, take note, relative amounts lang pwede natin hanapin dito and not the actual concentrations of the components. Okay? So bakit inverse ang tawag dito? So this is your inverse lever arm rule. Okay? Sinasabi lang dito guys, the moles of liquid is proportional to segment V apostrophe. Ano yung segment V apostrophe? Guys, ito yun. Diba? This segment is with respect to the vaporous curve. Again, okay? This segment V apostrophe is corresponding to the vaporous curve. Okay? With respect to the vaporous curve. Tapos yung moles of vapor nyo is proportional to the segment L apostrophe. Ito yun. Ito yun. Okay? So, this segment here, okay, is with respect to the liquidus curve. Diba? Okay. So later on, we will learn more on how to calculate the relative amounts of liquid and vapor. So guys, ang segment V apostrophe mo, okay, that is, tingnan nyo guys ha, V apostrophe, yung line na to, yung segment na to. So if you want to get the actual value of that segment here, that is just YA3 minus ZA. Oh, guys, ZA yung sa gitna, diba? Always. That is your segment V apostrophe. Okay? Tapos may specific value yan. O ma'am, bakit YA3 muna? Guys, syempre, mas malaki ang YA3, diba? It is greater compared to your ZA. That's why matik siya yung nasa unahan. Okay? So when we say segment L apostrophe, okay, that is between the ZA and the XA3, which is on your liquidus curve. So segment L apostrophe, that is from ZA minus XA. Clear guys? O bakit nauna si ZA? Syempre guys, mas malaki si ZA than XA3. Okay? Bawal kasi negative ang value ng mga segments nyo. Okay? Bawal yun. Again, dapat always positive. That's why ZA comes first minus XA3. And through these segments guys, pwede natin mahanap ang moles of liquid and moles of vapor. So later we will try that. Next guys, punta tayo sa point 4. Okay? At point 4 guys, we further decrease the pressure at this point. Anong tawag sa point na to guys? It is the dew point. Here, the last drop of liquid form. So, konti na lang, wala ka ng liquid at this point. Isang drop na lang guys, ang liquid mo. Again, isang drop na lang ang liquid mo. And you have mostly vapor at this point, at the dew point. So, we have to get the relative amounts or the mole fractions of components A and components B based on this point 4 here. So, the mole fraction of component A at point 4 is, again, reflects sa liquidus curve. Okay? To get the mole fraction of component A in the liquid phase. Oh, ito na yun. So, XA is equal to XA4. This is your XA4. Notice guys, di ba? Close to 0 na ang mole fraction ng component A in your liquid phase. And tama naman, di ba? Because at the dew point, the last drop of liquid form. So, dapat, at this point, puro vapor na lang. Kaya onting-onting na lang ang amount of A mo in your liquid phase. Okay? Now, what about the component B? So, guys, si XB4, the mole fraction of component B at point 4 is just equal to 1 minus XA4. Okay? And what about the mole fraction of component A at point 4 in the vapor phase? Again, reflect through the vapor curve. So, guys, this is your vapor curve, right? And it is being reflected sa ZA. Ayan na. So, the mole fraction of component A at point 4 in the vapor phase, right? That is equal to ZA, the overall composition of component A in the mixture. Okay? Lastly, guys, punta tayo sa point 5. At point 5, guys, purely vapor na lang meron ka, wala ka ng liquid. Therefore, the mole fraction of component A at point 5 is just equal to the overall composition of A in the mixture, and the mole fraction of component A at point 5 in the liquid phase is equal to 0 kasi wala ka ng liquid existing dito in this region. Clear, guys? I hope it's clear. Okay? So in relation to the lever arm rule, we can also calculate for the fraction of vapor through this equation, Za minus Xa3 divided by Ya3 minus Xa3. So when we say Za minus Xa3, it is from this to this. Okay? Kunwari at point 3. Guys, hindi yan strictly at point 3. Siyempre, example lang natin yung point 3 na yan para ma-visualize nyo. But again, to get the fraction of vapor ha, you have to reflect it to the segment L apostrophe. Bakit? Again, because of the inverse lever arm rule, dapat inverse. Kaya nag-reflect tayo sa segment L apostrophe. That is Za minus Xa3 divided by Ya3 minus Xa3. So ito na yung buong yun. Okay? Because we are looking at the fraction of vapor, okay, in the overall mixture. Okay? So basically ito guys, liquid plus vapor. Yung nasa denominator. Tapos yung nasa numerator, vapor. Again, hinapit yung fraction of vapor. For the fraction of liquid, again, inverse ulit. So magre-reflect tayo based sa segment V apostrophe. So Ya3, the fraction of liquid is equal to Ya3 minus Za, ito again, divided by the total mixture. So that is Ya3 minus Xa3. Okay? Basically, liquid, amount of liquid divided by liquid plus vapor. Okay? So later, mas ma-visualize yan. Okay? I hope it's clear, guys. Ayan. So let's try to solve. So for example, guys, okay, mag-assign tayo ng value sa ating 0.3 na mole fractions. 0.3 muna para ma-visualize natin. So at 0.3, the mole fraction of component A at 0.3 in the liquid phase, ito, let's say that is equal to 0.4. Tapos si Za naman, yung overall composition ni A in the mixture, okay, is equal to 0.55. Okay? Tapos, ang mole fraction naman, the component A at 0.3 in the vapor phase is equal to 0.8. Okay? So guys, you can determine this either from using a ruler, okay, or baka given yung values. Okay? So guys, how do we determine the number of moles of liquid and number of moles of vapor? Okay? So again, it is with the lever rule, segment V apostrophe divided by segment L apostrophe. Again, guys, they are inverse. Okay? So let's solve again. V apostrophe, that is just equal to Ya3 minus Ca, right? This line. Divided by segment L apostrophe. Ito yung line na to. So Za minus Xa3. So simply, substitute the values of your mole fractions. So NL over NV, that is equal to segment V apostrophe, that is 0.8 minus 0.55. Are you following? Divided by 0.55 minus 0.4. This is your segment L apostrophe. In solving, guys, you get 5/3. Ano ang interpretation nito? Okay? For every 3 moles of vapor, okay, there are 5 moles of liquid. Yun ang ibig sabihin niya. Okay? Anong interpretation natin dito, guys? The liquid phase, it is more abundant than the vapor phase, di ba? Okay? Bakit ito nangyayari? O tingnan nyo, 0.3, guys. Okay? This happens when the overall composition Za is closer to the liquid composition Xa. Ito. Di ba, guys? Si 0.55, closer siya to 0.4. That is why, ang implication yan, you have greater amounts of liquid than the amounts of vapor. Okay? Ganun yun. Oh, ma'am, ang concentrations or relative amounts ni A, component A and B, in the liquid phase and in the vapor phase. So guys, very easy lang yan. Okay? Susundan nyo lang ako. Sabi natin, di ba, guys? A, the moles of A in liquid is equal to 0.40. So ang interpretation yan, meron tayong 40% of A in liquid. So, ilang percent of B ang meron tayo in the liquid phase? So 100% minus 40%, that is 60% of B in liquid. So guys, sa 5 moles of liquid na ito, you have 40% of A in liquid phase and 60% of component B in liquid phase. Okay? So guys, paano yan? The moles of A in liquid is just 5 moles times 0.40, right? That is the mole fraction of A in the liquid phase. And that is equal to 2 moles. So may 2 moles ka of A in liquid phase. For the moles of B in liquid phase, that is 5 moles times 0.6. So you have 3 moles of component B in your liquid phase. Ganun na. Oh, what about sa vapor phase? Here guys, you have 3 moles of vapor. So sabi dito guys, the mole fraction of component A in the vapor phase at 0.3 is 0.8. So, anong meaning yan? 80% of A ang nasa vapor. So, 20% of component B ay in vapor. So, how do we get the moles of A in vapor? So, simply guys, moles of A in vapor is equal to 3 moles times 0.8. So, ano space, moles A in V. So, that is 3 moles times 0.8. That is equal to 2.4 moles of A in vapor. In vapor phase. Tapos, moles of B naman, okay, that is 3 moles times 0.2. Diba may 20% of B ka lang in vapor phase. And that is equal to 0.6 moles of B in the vapor phase. Ganon guys, ang interpretation. Okay? I hope it's clear. So let's proceed with the sample problem. Okay? Very simple lang. Find the fraction of vapor and fraction of liquid at 0.3 in the phase diagram below, given the following values for your Ya, Xa, and Za. Okay? So let's solve this together. So for the fraction of vapor, again guys, dapat inverse siya ng vapor, right? So dapat titingin ka sa segment L dito. Okay? Segment L. No? So again, this is your Za. So this is your Xa3. So Za, 0.55 minus Xa3. Again, dapat reflect tayo sa inverse, which is segment L apostrophe. So Xa3 is equal to 0.4 divided by the total liquid plus vapor. Again guys, hinahanap kasi natin fraction of vapor. Buksan natin fraction of vapor, edi fraction of vapor in the overall mixture. So dapat hanapin natin yung overall mixture, overall amounts at 0.3. Ito. So that is Ya3, itong 0.75 minus 0.4. Okay? So we get 0.43. Ang interpretation na we have 43% of vapor in the, meron tayong 43% of vapor in the overall mixture for at 0.3. Tapos naman, getting the fraction of liquid. Again guys, hinahanap natin fraction of liquid, dapat inverse yung numerator natin. So titingnan natin si segment V apostrophe. So that is Ya3 0.75 minus 0.55, diba? Your Za, divided by again the total amounts of liquid plus vapor at 0.3. So that's 0.75 minus 0.40. That is equal to 0.57. Ano ang interpretation ito? We have 57% of liquid in our overall mixture. So at 0.3 guys, 43% yan ay vapor. Tapos 57% yan ay liquid. Ganun lang. Okay? So again guys, tingnan nyo yung formula na to. Hindi siya exactly the same, diba? Sa lever rule. Okay? So these are different equations from our equations for this one. Diba? Iba yan magkaiba silang dalawa. So this one is different from this one. And this one is different from this one. Okay? Again guys, dito hinahanap natin fractions of vapor, fractions of liquid in the overall mixture. I hope it's clear guys. Ha? Kayang-kaya nyo to. Diba? Kayang-kaya nyo to. Now let's proceed to non-ideal liquid vapor mixtures. So we have two types. So that depends on whether or not the system positively or negatively deviates. Positively deviating system, we have this phase diagram niya, where we see that the vapor pressure, guys, yung curve na ito, is higher than the ideal vapor pressure. So ideal, guys, is yung mga broken ice. Okay? That is the positive deviation. We have a higher vapor pressure than the ideal. So for example, okay, if we mix ethanol and hexane as shown here, ayan, okay, you have a positively deviating system. Ito yung pinapakita sa phase diagram ito. Now what happened here? Okay, so for example, you mix ethanol and hexane, guys, you know that ethanol is polar and it only forms hydrogen bonds with itself, while hexane, it is non-polar and has weak one non-dispersion forces. So that when you mix them, diba, yung hydrogen bonds between ethanol molecules will get disrupted by the hexane. Pero guys, hexane, syempre, hindi niya ma-replace yung mga hydrogen bonding interactions na yun, diba? Because it is non-polar. Meanwhile, ethanol, it is polar, right? So yung new interactions between ethanol and hexane, they are much weaker compared to the original ones, which are the hydrogen bonding interactions between ethanol molecules and the one non-dispersion forces between hexane molecules. So guys, ano mangyayari kung weaker ang interactions ni ethanol and hexane? So the molecules will be less tightly held together. Ano mangyayari kung less tightly held? Then the molecules are, they get easier. It gets easier for them to escape into vapor. Kaya tataas ang ating vapor pressure than expected. Therefore, we have a positive deviation. Okay? So ano ang characteristics ng isang positively deviating system with a phase diagram such as this? Okay? So this, in terms of structure, okay, magkaiba yung structures ng mga molecules nyo. Diba? Because they have different IMFAs within them. For example, ethanol and hexane, they are completely different molecules with different structures. Si ethanol, it only has OH. Diba? Si hexane naman, it consists of carbon and hydrogen bonds. That's why it is non-polar, right? CH, diba? It is made of CH lang, therefore it is non-polar. Next, okay? So we usually see a positively deviating system if we have molecules that have different polarities. So diba? Si ethanol and hexane, they have different polarities. And what is the effect in the heat of mixing or delta H of mixing? So guys, it is positive. Bakit positive? Okay? Because it wants to take in heat. Okay? Okay? So positive ang ating delta mix H. Okay? Tapos positive rin ang ating delta mix V. Okay? Or the volume change. Meaning yan guys, mag-increase ang volume when we mix ethanol and hexane together. And that results in expansion. Okay? So for example guys, nag-mix ka ng 5 ml ni ethanol plus 5 ml ni hexane. Okay? So yung result yan guys, okay? Yung total volume nila ay more than 10 ml. Okay? Yun yung tinatawag na positive delta mix V or positive volume change. Okay? I hope that's clear, guys. Now, this is your negatively deviating system. So, balik na dito ng positive deviation. So, the vapor pressure of the solution, of the non-ideal solution, is lower compared to the ideal. Again, guys, yung ideal, yung broken lines. So, what happens? So, for example, we have acetone and water. So, si acetone, guys, and water, they actually mix completely, right, to form a homogeneous solution. Okay? Pero guys, hindi porket nag-mix sila together and they form a homogeneous solution, it doesn't mean that the vapor pressure will behave ideally. So, here's why they will form a negatively deviating system. So, first, okay, ang reason ay, yung interactions ng acetone with water ay very strong. Very strong. Stronger compared to the interactions of acetone with other acetone molecules, okay, and compared to the interactions of water with other molecules. So basically, guys, stronger interactions between acetone and water compared to the interactions of the individual molecules with themselves. Okay, so basically, guys, acetone, water interactions greater than acetone, and water interactions. Okay, ayun. So ano mangyayari kung ganun? Kung stronger attraction between acetone and water, then fewer molecules will escape into the vapor. Guys, gusto nila mag-mix with each other in the liquid phase. So fewer molecules of acetone, water, will go into the vapor. That's why we will get a vapor pressure lower than expected. Lower than the ideal. Okay? Yun yung the meaning ng negative deviation. So meron silang negative delta mix H, negative delta mix V. Okay? So basically guys, kung negative ang delta mix V mo, when you add 5 ml of acetone and 5 ml of water, you will have a mixture of acetone and water that is less than 10 ml. Okay? So ano nangyari? Negative ang delta mix V. Therefore, there is a contraction in the volume. Okay? So guys, pag sinabi natin negative yung delta mix H or yung enthalpy change, okay? Meaning guys, when acetone and water interacts, they will release heat. Therefore, it feels warm. Okay? Ayan. So tandaan guys, ang shape na ito, di ba? Ganyan siya. Okay. Meaning yan, negatively deviating system. Tandaan guys ha, ang shape ito. Okay? Now guys, let's move on to the distillation of mixtures. Okay? So guys, to know more about the types of distillation, kindly watch this video first.
In today's video, we're going to look at the two types of distillation that we can use to separate out mixtures that contain liquids. Let's start with simple distillation, which is used for separating out a liquid from a solution. For example, we could use simple distillation to separate pure water from seawater. Before we cover how it works though, we need to be familiar with the equipment. First, we have a flask that contains the solution or the liquid mixture that we're trying to separate, and the flask is sealed at the top of the bung so that no gas can escape. We then put a thermometer through the bung so that we can measure the temperature inside the flask. Next, we have our condenser, which consists of a main pipe surrounded by a water jacket, which contains a stream of continually flowing cold water, with the water being fed into the water jacket at the bottom and coming out at the top. Then beneath the end of our condenser, we'll have some sort of beaker to capture pure liquid. And finally, we're going to need some sort of heating device, like a Bunsen burner, which we place under the flask. Our first step is to heat up the mixture, so that the liquid that we want evaporates. As it rises to the top of the flask, the pressure will force it down the condenser. And because we're pumping cold water through the water jacket, the vapor will cool and condense into liquid form, which will then run down the pipe and collect in the beaker. So in our case, as we heat the seawater, we'll get more and more pure distilled water, until eventually all we have left in the flask is salt. Now imagine instead that we were trying this technique with a different mixture, one containing some different liquids, like methanol, ethanol, and propanol. Because these liquids all have similar boiling points, when we heat them, more than one of them will evaporate, and they won't be separated into pure substances. In this case, we'd have to use a different technique called fractional distillation, which is the main technique used for separating mixtures of liquids. The equipment for this is pretty similar, but instead of the gas passing straight from the flask into the condenser, the vapors have to first pass through a fractionating column, which has two key features. One is that it's full of little glass rods, which provide a really high surface area. And the other is that because the column is so tall, it's actually cool at the top and at the bottom. To understand why this is important, let's imagine that we were trying to separate those three liquids that we mentioned before, methanol, ethanol, and propanol, which all have similar boiling points, although you don't need to remember them. And before we continue, just be aware that in your life, these would all be colours, not green. We're just showing them as green to make it easier to follow along. Now, because methanol has the lowest boiling point, we'd heat the mixture to around 65 degrees first. This would cause the methanol to evaporate, and then rises up the fractionating column. It would then pass into the condenser, and condense into liquid methanol, which would then collect in our beaker. However, just by chance, some of the ethanol and maybe even propanol would also evaporate. But as they rise up the fractionating column and come into contact with all those glass rods, which are much cooler than the boiling point, they condense back into liquid form and fall back into the flask. This means that the only liquid that will be on the other side will be pure methanol. The next step would be to do the same thing all over again for ethanol by raising the temperature to around 78 degrees Celsius, which will allow us to evaporate off the ethanol. At this point, all that should be left is the propanol, so we could just assume that what we have in the flask is pure propanol. Or we could raise the temperature again to boil up the propanol, just to make sure. Anyway,
So guys, the video summarizes the differences between simple distillation and fractional distillation. However, ang focus natin dito ay ang fractional distillation because we are concerned with the distillation of liquid mixtures. So here guys, we have a temperature composition phase diagram and we use it in analyzing fractional distillation. Okay? So when we say temperature composition guys, ang temperature natin this time ang nasa y-axis. So meaning guys, this is your vapor. And this is your liquid. Okay? Diba? As temperature increases, it favors vapor formation, and as temperature decreases, it favors liquid formation. Okay? So what happens? So for example, you have a mixture with a component A and B. Diba? Components A and B. So si A, it is more volatile than B. Now, when you heat the mixture guys, A will turn into vapor more easily. Kasi nga mas volatile siya. Okay? So, while A will vaporize, okay? Tataas yung temperature, therefore dito na siya. Okay? Sorry. So, A will rise at the fractionating column. Okay? While B will stay in the liquid more. Diba? Meron tayong flash dyan. Magsistay dyan si B. Okay? Because it is less volatile. Now guys, in the fractionating column, then si A ang nag-rise to the fractionating column. A will evaporate, as you can see here. So, pupunta siya from liquid, magiging vapor na siya. Pupunta na siya sa vapor curve. Okay? Dahil dyan, it rose up to the column. Again, A has evaporated. Now, as it rises guys, okay, A will condense. A will condense, and then after condense it, guys, we can evaporate it again. For example, we can evaporate A again, and then it will condense again. Now guys, bakit ginagawa to in multiple stages? This is to ensure that every time we do the evaporation and condensation cycle, as you evaporate and as you condense in every stage, diba, the liquid, okay, gets more and more enriched with A. Again, yung liquid mixture nyo gets more and more enriched with A. Okay? Or in other words, nag-increase ang concentration ng A sa ating liquid mixture. Okay? So, at the very top of the column, the vapor that is rich in A, kunwari sa last stage ka na, sa third stage ka na, okay, the vapor will then pass through a condenser. Okay, so ito yun. Dito siya, di ba? Nag-evaporate si A. Tapos rich in A na yan talaga. It will pass through a condenser in order to be reverted back into a liquid. Okay? Now, this liquid will be collected. Yung liquid na yan is what we call the distillate. Again, this is collected from the condensation of the vapor at the final stage of the fractional distillation. Okay? So the vapor, again, it goes down into a liquid and then the liquid collected is the distillate. Okay? And the distillate is mostly pure in A. And yung natira naman guys, okay, yung leftover liquid sa flask is your residue. Okay? So that is the basic concept of the distillation of mixtures. Okay? Now guys, in relation to the distillation of mixtures, we have what we call the azeotropes. So azeotropes, they form, okay, when a mixture with components A and B, they evaporate without changing its composition. So, kapag nag-evaporate and nag-condense ka ng isang mixture containing A and B, the mole fraction in the liquid and vapor phase, which is X azeo, it is always equal. Therefore, distillation is not possible. So tingnan nyo to guys, this is a high boiling azeotrope. So for example, the mole fraction of component A is 0.30. Okay, 0.30. Tapos yung initial temperature mo nandito ka. Tapos, iinitin mo ang mixture mo, iinitin mo until it reaches the final temperature here. Tf is T azeo. What happens guys is that the liquid mixture has evaporated and it has transformed into a vapor. Notice guys that as it transformed into a vapor, same pa rin ang kanyang what? Mole fraction. Same pa rin ang mole fraction ni component A. Now guys, tingnan natin kung i-condense natin ang vapor na ito back as a liquid. Oh guys, condense natin. Ito, condense na siya at this point. Guys, same pa rin ang ating mole fraction of component A. It is still 0.30. Diba guys, sa distillation of mixtures, as we do the evaporation and condensation cycle guys, diba dapat habang nagko-condense tayo, nag-evaporate tayo, diba? Yung mole fraction ng component mo dapat nag-i-increase. Diba? Dapat yung liquid mo is being more enriched with A. Yung collected liquid mo as you condense, dapat more enriched with A. However, this is not the case guys. Hindi nagbago. Hindi dumagdag ang mole fraction niya. Hindi nagbago. Therefore, parang na naglolokohan dito. Okay? That's why for an azeotrope, it is impossible to do distillation. So specifically guys, for a high boiling azeotrope, meaning dito, yung mixture na yan is harder to boil. Okay? And this is a negative deviation from Raoult's law. Why? Because the molecules, they will attract each other more. So let's say we have components A and B, these molecules, okay, they have stronger attractions compared to their individual attractions. So stronger ang A and B compared to the interactions between A and B and B. Okay. Now what happens with the vapor pressure? So that reduces the vapor pressure of the mixture. Okay? And therefore, fewer molecules na nag-escape sa vapor phase. So dahil dyan guys, kailangan natin ng much higher boiling point, T azeo, okay, in order to vaporize the liquid mixture. Okay? Again, because the vapor pressure is low, because the molecules are held more tightly in the liquid phase. So kailangan natin taasan ang ating boiling point. So for example guys, we have 80% water and 20% HCl. Okay? So this mixture guys boils at 110 degrees Celsius. Okay? Which is higher than the boiling points of water and HCl as themselves. Again, its boiling temperature, yung mixture na to, it is higher compared to the boiling point of pure water and the boiling point of pure HCl. So ganun din dito guys, as you can see here, the boiling point of the mixture is higher compared to the boiling point of pure A and pure B. Okay? Ganun na. Okay, good. So now here we have a low boiling azeotrope. So this time guys, low boiling. Okay? Ang meaning nito guys, easier to boil ang mixture. Okay? So same concept pa rin where as we vaporize and condense, di ba? Same pa rin ang mole fraction ng component A mo. Okay? So okay, di nagbabago. However, the boiling point is lower than pure B and pure A. Bakit? Okay? Because the AB molecules, they have weaker attractions than the individual AA and BB interactions. Okay? Bakit guys? Because they are more volatile. Therefore, they evaporate easily. That's why they have weaker AB interactions in the liquid phase. That's why you would only need a lower boiling point in order to boil or vaporize the mixture. So for example, we have 96% ethanol and 4% water. Guys, it boils at 78.1 degrees Celsius. This is lower than the boiling point of pure ethanol and the boiling point of pure water. Okay? Yun yung tinatawag nating low boiling isotherm. Tingnan guys, ito ang boiling point ni pure A, ito ang boiling point ni pure B. However, again, their mixture has a lower boiling point. Again, because of the weak AB interactions. Okay? So tandaan lang, pag high boiling, strong attraction, therefore harder to boil. Tapos pag low boiling, guys, weak attraction, therefore easier to boil. Okay? Okay. Let's proceed. Ayan. So let's move on to the next part of our discussion on the liquid-liquid equilibrium. So guys, there are two types. Okay? We have miscible liquids, fully miscible liquids, and fully immiscible liquids. Okay? And later on, we will discuss partially miscible liquids. Okay? So for completely miscible liquids, guys, okay? So for example, alcohol and water, the two components uniformly mix in the liquid phase regardless of their amount. Okay? That's why you have a single homogeneous phase formed. Okay? Bakit miscible? Because the two molecules, they are similar in terms of polarity and IMF phase. So for example, alcohol and water, they both have hydrogen bonding, right? And they are both polar. So other examples of completely miscible liquids are water and ethanol, acetyl and methanol, and benzene and toluene. Okay? Now guys, take note that there is no equilibrium between the two phases of alcohol and water. Kasi one phase lang sila, di ba? Again, they are one homogeneous phase. That's why there is no equilibrium between two phases. Kasi nasa isang phase lang sila. Next, for completely immiscible liquids, guys, the two components do not mix at all. So for example, si oil and water, right? And therefore, they have distinct phase boundaries. Ito si oil, ito si H2O. So the immiscibility is due to their differing polarity or IMF phase. So si oil, guys, di ba? It is non-polar, water is polar. That's why they are immiscible. Okay? And ang result niyan is the liquids will separate into two layers. So yung denser liquid, which is oil, is above the less dense one, which is water. Okay? So in this case, guys, the two components here will behave individually. They will not interact with each other kasi hindi na sila miscible. So wala tayong equilibrium between these two distinct phases. Okay? So other examples of completely immiscible substances include mercury plus H2O. Okay? So now we also have what we call binary partially miscible liquids. So sila guys ang may liquid-liquid equilibrium phase diagram. So like miscible liquids that mix completely or immiscible liquids that don't mix at all. Okay? So yung partially miscible liquids naman, okay, they exhibit a limited solubility. Okay? That's why we will have our heterogeneous mixture with distinct layers. So for example natin dito ay si water plus triethylamine, ano pa ba? Water plus nicotine, and nitrobenzene plus hexane. Okay? Pag binary guys, again, that meaning yan between two liquids, partially miscible, meaning yan, the two liquids only mix a little bit, pero not completely. Okay? Another simple example, we have water and phenol. So pag pinorma yan together guys, some of the phenol will mix with water, and some of the phenol will not mix with water. So that's why you will end up with two layers, each containing a bit of both liquids. So later we will see that. Okay? So guys, at low temperatures, in general, yung mga partially miscible liquids, they don't mix as much. Okay? You will see distinct two layers. However, as you increase the temperature, they will start to mix better. So guys, there's a temperature that we call the critical solution temperature, where they will be able to mix completely. But above that, they will become fully miscible. Again, above the critical temperature, they will be fully miscible. Therefore, you will only have one layer in that case. Okay? So to simulate a partially miscible liquids, kindly watch this video, guys.
In this screencast, I'm going to briefly describe how to use an interactive simulation for partially miscible liquids. In this simulation, there are two liquids that we mixed, but they only completely mixed over a certain composition and temperature range. The simulation is on the LearnChem site at the link given here, and if we look at a snapshot of the simulation, you can see that in this region, outside of this envelope, we have complete miscibility. But within the envelope, point represented by the black dot, what we have are two phases. One phase is majority of component B, so the mole fraction of A is only 0.24. The other phase is majority component A, mole fraction 0.72. And the boxes above them represent how much of A and how much of B, the size are proportional to the amounts. And then the size of the boxes on the right, these are two phases. One phase, beta phase, has mostly the blue molecules, and the alpha phase has majority green molecules. We can change the location of this black dot by moving the slider for temperature, moving the slider for mole fraction. So let's look at this simulation. So if I, for example, change the mole fraction, so I'm mostly mixing B, then you can see this box is large compared to A. And then the two phases, the amount of alpha phase is very small. That's proportional to this length here. Amount of beta phase, much larger. And the relative colors are proportional to the mole fractions in those phases. And then I go the other way. Now the alpha phase is much larger. Beta phase is much smaller. If I raise the temperature, I eventually get to the point where we have one phase, so the molecules are completely miscible in this region. So the idea is that over some range of temperature and mole fraction, we have phase separation. Outside of that range, we have complete miscibility for this binary mixture.
Very cool, right? So basically, that is the concept of binary partially miscible liquids. Pero guys, kung hindi nyo nagets yun, okay, ito explain ko sa inyo, okay? So, let's say guys, meron kayong components A and B, okay? Nung una, meron kayong purely A. So, you only have one phase, which is the A phase. So, si A ito. Now guys, ang gagawin ko guys, magdadagdag ako ng onting B. So, gawin natin pink yan. Onting B na liquid. Okay? So, ano mangyayari? Kanina, meron tayong A, diba? Ito yun. Nag-add ako ng onting B, guys. Okay? Ito na siya. So, we have here B in A. So, we have a little bit of B in A. And we call this the alpha phase. Kasi meron tayong B in mostly A. Again, guys, madami dapat yung A mo, pero onti lang si B. Yan ang tinatawag nating alpha phase. Okay? So the phase here is equal to 1. Again, alpha phase. Okay? Now guys, what if magdadagdag ako ng mas maraming B? So guys, kung A and B, they are partially miscible. Okay? Nung una dito kasi guys, miscible pa si B. Okay? A kasi onti pa lang ginamit. Onti pa lang minix mo kay A. However, if you add more and more and more of B, okay, A has a limited solubility with B. Okay? So ano mangyayari dyan? So magkakaroon ka ng A dito, di ba? So some of it, of course, nag-mix siya with B. Diba? Some of it. However guys, not all of B will be miscible with A. Again, there is a limited solubility. Yun yung concept ng partially miscible. So magkakaroon ka ng two distinct layers. Okay? So yung other layer na to ay si B. Now guys, sa layer na to, sa B layer na to, you will have some amounts of A. Some amounts of A. So dito guys, nagkakaroon tayo ng lipatan ng amounts of liquids A and B with each other. Okay? Lipatan. Diba? Because A and B, they are partially miscible with each other. Okay? So may lipatan. So here guys, we have ito guys, A in B ang tawag dito na layer, A in B. And this is your beta phase. So you have two phases guys. That is the alpha phase and the beta phase. So yung alpha phase guys, you have B in A. And sa beta phase guys, you have some A in B. Again, alpha phase, some B in A. Beta phase, some A in B. Here, yun yung alpha and beta phases nyo. Then guys, what if ang gagawin ko naman, mag-add ako ng super daming B, as in super daming B. So much that B, okay, will able to accept all amounts of A. Mag-add ako ng B guys, magiging, what? Can you guess? So this will be B. Napakarami na yan. And then, miscible na dyan ang all amounts of A. Miscible na dyan ang all amounts of A. So here guys, in this case, B is equals to 1. And ang present na phase natin ay si beta phase lang. Because again, nagdagdag ka ng maraming B. So mangyari ay you have some A in B. In this, okay? So again, nagdagdag ka ng maraming B. Oh guys, what if magdagdag pa ako ng mas maraming B? Okay? Magiging negligible na ang some amount of A. So magiging pink na lang to guys. This will only be purely B because super dami na nang dinagdag mong B. So ang phase ito ay 1. And the phase is B phase. B na, hindi na beta. Kasi, again, nagdagdag ka ng napakaraming B to the point na negligible na ang amount of liquid A. Kaya ang phase mo ay si B na lang, letter B. Ganon ang concept ng ating binary partially miscible liquids. Okay? Now, we actually have three types of binary partially miscible liquids depending on their critical temperature. Okay? So here, with upper critical temperature, okay, the two liquids will become fully miscible. So for example, guys, in this phase diagram, okay, on the left side, you have very pure A, and on the right side, you have a very pure liquid B. So on this side, and on this side, you have the alpha and beta phases. Okay? And in this curve, within this curve, you have two coexisting phases. Yun ang alpha and beta phases nyo. Now guys, when the liquid mixture, diba? Example, we increase and increase the temperature. Okay? If we increase the temperature above the upper critical temperature, right, increase ka ng temp, tapos above critical temperature na siya. Now, liquids A and B will become completely miscible. Again, above the critical temperature here, our liquids A and B will become completely miscible. Ang example natin dito ay si hexane and nitrobenzene. Second type is with lower critical temperature. So here naman guys, we have two liquids. So for example, we have water and triethylamine. Okay? Here, there exists two phases, again, alpha and beta phases. Now, when we decrease and decrease the temperature, okay, and if the temperature is now lower than the critical temperature, so nandito na yan. So the two liquids will become completely miscible. Again, example natin dito ay si water and triethylamine. And lastly, we have even weirder liquid mixtures with both upper and lower critical temperatures. So for example, again, you have here your alpha and beta phases. Okay? And this is your liquid A and liquid B. So on the left side means that you have pure A, and on the left and the right side you have pure B. Okay? So above the upper critical temperature and below the lower critical temperature. So dito guys, okay, liquids A and B will become completely miscible. So example natin dito ay si water plus nicotine. Okay? Now let's move on to, so there are two types of distillation of partially miscible liquids. So first, boiling can occur before the two liquids can become fully miscible, while boiling can also occur after the two liquids become completely miscible. So for the boiling before being miscible, here, okay, tingnan nyo ang shape ng inyong phase diagram, diba guys? It is a Pikachu shape, diba? So nangyayari dito, yung dalawang liquids nyo, they will individually vaporize, okay? So hindi na sila maghahalo-halo. So for example, your alpha phase is here, your beta phase is here, okay? And on this region, you have two coexisting phases, si alpha and si beta. So what happens is that at the critical point, dito yan, the alpha phase will boil separately from the beta phase. So the beta phase will also separately boil from your alpha phase. So when you reach the critical temperature here, okay, dito, and on this region, you will have the alpha phase, okay? So some alpha liquid, so some liquid rich in alpha phase, and vapor. So dito naman, you have beta phase and vapor, okay? Tapos dito naman, fully vapor. Okay? Again guys, boiling occurs while they are still partially miscible. So hindi sila mag-mix bago sila mag-boil. Ang example natin dito ay si water and diethyl ether. So tandaan nyo lang guys, ang shape ng ating phase diagram for boiling before being miscible. Pikachu yan, okay? Next, boiling after being miscible. Okay? So here guys, we can actually combine the liquid-liquid equilibrium, ito, and your liquid-vapor equilibrium, yung nasa taas. Okay? Now this line here guys, ito yung tinatawag yung critical point. So here, you have your alpha phase and your beta phase. And on this region, you have the two coexisting phases, alpha and beta. Now, when you increase and increase the temperature of your mixture until the critical point, now above the critical point, guys, you will form one uniform phase. Okay? In short, guys, dito, completely miscible na ang inyong two liquids. Okay? Again, above the critical point, magiging completely immiscible na ang dalawang phases. Now, if your liquid is here, and you increase the temperature even further, you will reach the liquidus curve. Ito yung liquidus curve, diba? Once you have reached the liquidus curve, what happens? Okay? Vapor starts to form. Right? Boiling starts to occur as you reach the liquidus curve. As you further increase the temperature, the liquid then transforms to vapor. So dito na ang vapor region, you guys. Dito. Okay? So what can we say about that? Boiling occurred after the two liquids became fully miscible. Ang example natin dito ay si water and phenol. So tandaan na, okay, class, nag-fully mix muna ang liquids such as water and phenol before they will boil. Now guys, we have this type of partially miscible liquids and we call this ternary partially miscible liquids. So in the ternary partially miscible liquid system, okay, one or two component pairs are completely miscible. Okay, while the remaining pair, so within the curve, is partially miscible. And in-illustrate ito ng Gibbs crucible ternary phase diagram as shown below. So let's say guys, you have three liquids, ethanol, benzene, and water. Okay, so let's determine the parts of your phase diagram here. So on the corners, within the corners are your liquids. So at this top corner, you have 100% ethanol. Now, how do you know if the amount of ethanol decreases? So you will see it as you go down the triangle here. So if you have 100% ethanol here, you have 90% here, 80%, 70%, 60%, and so on and so forth. So ito yung titignan nyo na lang, okay? For the concentration or for the relative amounts for ethanol. And then for benzene naman, okay? On this left corner, you have 100% benzene. Okay? So you have 100% benzene here. Then, as you go upwards, dito sa triangle, dito sa side na to, you have 90% benzene, 80% benzene, 70% benzene, and so on and so forth. Okay? Again, you will refer to this line for this corner here. And then for the rightmost corner here, you have 100% water. Therefore, as you go to the left of this horizontal line here, dito guys, okay, the relative amounts of water will decrease. So you have here 90% water, 80% water, 70% water, and so on and so forth. Now, okay, so the lines which is intersecting at the delta point, okay, these crosses the binodal curve. Again, the lines here, the blue lines, okay, which intersect at the delta point, they cross the binodal curve at 2 points. Ito ang ginagamit natin in lever rule. Ito yung ginagamit natin in determining the relative amounts of our liquids. Okay? So guys, ito yung tinatawag nating tie lines. This time your tie lines are diagonal. Hindi na sila naka-horizontal. So when we say binodal curve here, ang dark red, it outlines a region where two liquid phases coexist. So that is, tingnan nyo, nasa ang binodal curve, diba? It is between benzene and water. Therefore, within the binodal curve, you have two coexisting liquids, that is benzene and water. And within this region, you have partially miscible benzene and water. Now, what can we say outside the binodal curve? So outside the binodal curve, only one phase exists. Again, outside the curve, only one phase exists. So, hindi kasama si A, diba? Hindi kasama si A in the coexistence of these two liquids within the binodal curve because, guys, kasama lang si A pag kunwari meron tong binodal curve dito or may binodal curve dito. Guys, for this phase diagram, wala. Therefore, hindi kasama si A in the coexistence of partially miscible liquids. So, what can we say outside the curve? Ethanol and benzene, they are outside the curve, right? Outside the binodal curve. Therefore, they are completely miscible. Well, ethanol and water, they are also outside the binodal curve. Therefore, they are also completely miscible. Okay? Si benzene and water lang ang partially miscible with each other. Okay? That's why they coexist in this binodal curve here. Okay? Again, the tie lines, yung mga diagonal, these connect the compositions of the two coexisting phases, so that is benzene and water. Kita nyo guys, meron tayong benzene dito and water. And ito ang tie line, just right between them. And you can just easily calculate the relative amounts based on tie lines. Now, what is the plate point? So the plate point, okay, let's say the plate point is over here. Now, the plate point is the point at which the two phases become indistinguishable because they contain equal amounts of both phases. Again, at the plate point, hindi mo na ma-distinguish basically ang benzene and water from each other. Okay? At this point, they have equal amounts. So may equal amounts of benzene sa amounts ni water. So, for example, we have a point inside the binodal curve, this point. And then we have to determine the relative amounts of your liquids here. So, you just have to look at the lines perpendicular to this point. So, first tingnan natin ang relative amounts ni ethanol. Okay? So, again guys, makikita natin dito ang composition ni ethanol sa right side. So, if you have 100% ethanol here, and you have a point here, then just draw a line. Just draw a line here that reflects the composition line for ethanol. And you will see that the composition of ethanol at this point in the binodal curve is 30%. Diba? Kasi perpendicular siya. Next, we determine the composition or relative amount of benzene. Again, dito natin makikita ang relative amount of benzene kasi nandito si 100% benzene. So, tingnan nyo lang guys yung mga guidelines dito, yung mga broken lines. And you will see that at this point on the binodal curve, the relative amount of benzene is 40%. Diba? Kita nyo guys, they are perpendicular from one another. And lastly, for the composition of water, okay, again, we refer to this line here. You have 100% water here. So, tingnan nyo lang guys, based sa guidelines, yung mga broken lines na yan, kung anong line ang i-follow natin. So here, ito. Okay? And we see here that our composition for water is 30%. Okay? O bakit hindi 60%? Kasi hindi na sila perpendicular sa isa't isa, diba? Kung nandyan ang ating concentration or relative amount for water, therefore, ang tama ay nandito. Okay? Also, it is following the lines, the broken lines. Again guys, it's important that we follow the broken lines. So, at this point on the binodal curve, you have 40% benzene, 30% water, and 30% ethanol. So, anong ibig sabihin nito? The mixture will separate into two layers. Again, yung mixture mo ng benzene and water will separate into two layers because they are partially miscible. Okay? And then the tie lines here, okay, it will determine the relative amounts, okay, or what each layer is made of. Ayan. Guys, marunong tayo mag-determine ng relative amounts sa ating ternary partially miscible liquid diagram or Gibbs-Ruzicum diagram. Okay? Very easy. Ayan. Now let's move on to solid-liquid equilibrium. So we have three types of binary solid liquid systems. Okay? In general, guys, tandaan, okay, when you have a low temperature, it favors solid formation. Okay, again, low temperature favors solid formation because your molecules will become more packed, diba? More ordered in a certain volume. Therefore, okay, again, lower temperature favors solid formation. So for the first type, we have the binary miscible solids. Okay? So for the binary completely miscible solids, okay, you have two solids that mix perfectly at all ratios. Okay? And magpo-form sila ng one single solid phase, parang alloy. Okay? So let's look at this graph. Here on the x-axis, you have the composition. Okay? So that is from 0% A, right, 0% B to 100% B. Okay? And the y-axis, you have the temperature. Now, the smooth curve here shows how the melting point changes between pure A and pure B. Okay? And here you have what's called the liquidus line. So guys, ito yung liquidus line nyo. Yung nasa taas. Okay? The top curve. And above the liquidus line here, the mixture is all liquid or melt. Now, sa bottom curve naman, you have your solidus line. Solidus. And below the solidus line, the mixture is all solid. Okay? Now, between them, you have partial melting. So you have some solid and some liquid or melt. Okay? Again, for binary completely miscible solids, you have only one phase in the solids, and there is no layering nor separation of solids. So for example, we have copper and nickel alloy. That is an example of miscible solid. Okay? And next we have the binary completely immiscible solid. So ito ang kanyang phase diagram, guys. So last year sa board exam, tinanong sila kung ano ang diagram, ang figure ng diagram for completely immiscible solids or partially immiscible solids, guys. So make sure na alam nyo yung shape. Okay? Alam nyo, and aware kayo sa shape. Memorize nyo ang shape ng phase diagrams nila. And as well as the other liquid-liquid equilibrium phase diagrams, or kaya yung LVE or liquid vapor equilibrium phase diagrams. Okay? So for a binary completely immiscible solid, okay, you have a eutectic point. So this is the eutectic point. The eutectic point. Okay? Then your liquid or your solid gets easily melted. So yun yung dinedescribe ng ating eutectic point. Okay? At this point, your solid gets easily melted. Yeah. So for this binary completely immiscible solid phase diagram, okay, the two components, they will behave as distinct solid phases. So makikita natin, guys, that when component A melts, okay, it has different melting temperature compared to component B. Okay? And vice versa. Diba? Magkakaiba sila ng melting points. Okay ba to? Let's say ito yung kay B and ito yung kay A. Okay? Again, they have different melting points. And that is because they are completely immiscible and they behave as distinct solid phases. Again, guys, when you see eutectic point, it is the temperature at which your solid becomes the most easily melted. Okay? So for example, for a binary completely immiscible solids, you have a mixture of two different crystals. And lastly, this is the shape of the diagram for a partially immiscible solid. So here you have a mixture of the two phases. So meron kang distinct A-rich phase and B-rich phase. So again, meron ka dito yung alpha phase mo. And here you have your alpha and beta phases. Dito naman you have alpha and liquid, and you have beta and liquid, diba? Notice, guys, when they melt, they form alpha phase and liquid, and beta phase and liquid. Now, above this curve, you have melt or liquid. Okay? Again, for a binary partially immiscible solid, okay, you have also alpha and beta phases. Kasi partially immiscible sila. Okay? Or partially miscible sila. Then guys, you don't have to analyze ano yung nangyayaring melting within the phase diagram. Okay? Pinaka-important na alam nyo ang shape ng phase diagram of these types of solids. Okay? Again, this is for the binary partially miscible or immiscible solids. Okay? So ano examples natin? For binary completely immiscible solids, our example is, any guess, guys? Sige nga. May alam tayo. So it is actually lead and silver chloride. So we have lead and silver chloride. Okay? This led to a completely immiscible solid system. And then for partially immiscible solids, our example is metal-metal or metal-ceramic systems. Again, for binary partially immiscible solids, they will mix a little bit but not completely. There is a certain limit. Okay? So, again, to clarify, guys, tandaan, this is your solidus line. Tapos ito ang liquidus line. Okay? So, when you pass through the solidus line, then you have some solid that has melted. Kaya dito, guys, meron kang alpha na solid, then this is alpha solid, and you have a liquid. And then here, again, this is the solidus curve, the solidus line. So, when you pass through this line, okay, then some solid has melted to liquid. So, here, there exists a beta solid and a liquid. Okay? Then above the liquidus curve, ito, we only have melt or liquid. Okay? Again, the eutectic point describes the temperature at which the mixture will be easily melted. So, yun. Okay? Now let's move on to reacting systems. So reacting systems are binary mixtures which react to form more stable compounds. So for example, we can see this in the semiconductors of beryllium and arsenic. Okay? And there are two types of reacting systems depending on the process of melting. So we have congruent melting. So melting here occurs without a change in composition. Okay? So meaning, guys, the composition of the liquid form of AB is the same as that in its solid form. And we'll also discuss incongruent melting. Here, the pure AB, it will melt, but not as itself in the liquid phase. Again, it will melt, but not as itself in the liquid phase. It might be unstable in its liquid form. Okay? So let's differentiate. First, we have the congruent melting. So again, the melting occurs without a change in the composition. Okay? So the composition of the liquid form of AB is the same as that in its solid form. That's why, okay, ABS pa rin. Okay? Diba? Sabi dito, it is a liquid with 50% A and 50% B. Okay? Meaning yun, guys, kung yung solid nyo ay 50% A and 50% B, if it melts, it still has 50% A and 50% B as a liquid. Again, recall this na, dapat memorize ang ating phase diagram for congruent melting. Next, we have incongruent melting. So in this case, the pure AB, okay, it will melt but not as itself in the liquid phase. So keep guys, here we have A, the solid, and AB2. Okay? So that's between A and B, the solids. Okay? When it reaches the solid curve here, you produce melt plus A solid and melt plus AB2 solid. Okay? Again, this is your peritectic point. And then above the liquid curve, liquid is attained, diba? Or melt is attained, where P is equals to 1. Okay? So ganun mag-analyze guys ng phase diagram, okay? I hope it's clear. So, notice you guys, sa incongruent method, meron tayong tinatawag na peritectic reaction. Now, what is a peritectic reaction? So, in peritectic reactions, okay, there is a special reaction point. Okay? A special reaction point. And here, at the peritectic point, the liquid phase and a solid phase, let's say B, again, a liquid phase and a solid phase B, they will react to form a new solid phase A. So, ano nangyari? In peritectic incongruent melting, a solid melts into a liquid and a new solid. Again, guys, ang product natin dito, the solid, it will melt into a liquid and a new solid. Okay? So, yung liquid and new solid mo, dapat meron silang different identities than the original solid. Okay? And guys, because the pure AB has melted but not as itself in the liquid phase. Okay? This is the phase diagram for incongruent melting. Now, here you have a phase diagram for a liquid with two soluble salts. So, your liquid is water and your soluble salts is ammonium chloride and ammonium sulfate. So, we can determine the behavior of the solubility of these salts in water based on this phase diagram. Okay? So, let's get to phase 1 or region 1. Region 1, ito. Guys, it is very near to water. Therefore, you have an unsaturated solution at region 1. Okay? So, at region 2, okay, P is equals to 2, right? And it corresponds to the saturated solution with respect to ammonium chloride. Okay? Note guys, nasa region na to, region 2, may onting laman pa ito ng ammonium sulfate. Okay? So, dito, nung nangyayari, if you have a saturated solution, you have a liquid, okay, and the formation of ammonium chloride crystals. Okay? Kasi, again, saturated na ang ammonium sulfate solution natin. Okay? So, for region 3 here, you have a saturated solution also, with respect to ammonium sulfate this time. And ang region na to, ay may konting laman ng ammonium chloride. So, ganun din here guys. At region 3, we have liquid and formation of ammonium sulfate crystals. Diba? Kasi again, saturated na ang ammonium sulfate natin. Again, ang product natin at region 3 is the same. We have liquid and the formation of ammonium sulfate crystals kasi saturated na ang ammonium sulfate natin. Lastly, for region 4 here, E is equals to 3. So, it consists of solid ammonium chloride, NH42, SO4 crystals. And the third one is the unsaturated solution between NH4Cl and NH4SO4. Okay, so again, list natin yan para mas maayos. So at region 4, you have 1 NH4Cl solid, 2 NH42SO4 solid, and third, okay, is the unsaturated solution between ammonium chloride and ammonium sulfate. Okay, again, we have here all, okay, the solid, the crystals, and the unsaturated solution between ammonium chloride and ammonium sulfate. Okay, I hope it's clear, guys. So, naman sa corners. Here you have pure water. Here you have pure ammonium chloride. And here you have pure ammonium sulfate. Okay? I hope it's clear. So, yun lang naman yung basic parts ng phase diagram na ito. Okay? Don't overanalyze it, okay? Ayan, pas na guys. So, let's answer these questions. So, let's answer. So, it is a graph that shows the physical state of water under different temperature and pressure conditions. Guys, ano kaya to? Tama, it is a phase diagram of water. Next, it is the endpoint of the liquid gas curve. And beyond this point, a supercritical fluid forms in which liquid and gas phases become indistinguishable. Ano kaya yun, guys? Yes, very good. That is your critical point. Next, it provides a number of intensive variables that can independently change while the number of phases is retained in equilibrium. That is your Gibbs phase rule. Okay? Next, it estimates how vapor pressure changes with temperature during a phase transition. Oh, anong type of equation nga to, guys? Yes, it is a Clausius-Clapeyron equation. Lastly, it forms when a mixture evaporates without changing its composition. Anong tawag dito, guys? Species. Very good. That is an azeotropic species. Okay? Yay. So, congratulations, guys. We are done with crash course on phase equilibrium. Good job, guys. Diba? So, ang tip ko on phase equilibrium, guys, as long as alam niyo yung drawing ng phase diagram and gets nyo ang nangyayari in liquid-liquid equilibrium, liquid-vapor equilibrium, and solid-liquid equilibrium, is kayang-kaya nyo ang phase equilibrium. Okay? Again, it takes a lot of practice and a lot of visualization. Kailangan nyo tumingin ng other phase diagrams in order to further understand the phase equilibrium. Okay? Okay. Now you're ready to answer your physical chemistry practice test 7. So these are for 10 items. Okay? And you have 25 minutes to answer. Okay? So guys, you're done with crash course 1, crash course 2, 3, 4, 5, 6, and 7. So congratulations, guys. Okay? You only have 3 crash courses left for physical chemistry. Okay? So again, this is your updated schedule on A. So class, remember that your crash course 1, it corresponds to quantum mechanics 1 and 2. Okay? So inayos na namin yung order ng crash courses nyo. But the PT numbers, they are still the same. Okay? So we will have our next PT discussion on July 20. Okay? See you there. And we will discuss here the answers to your practice test 3, practice test 4, and practice test 5. And then again, on July 27, we will release your question set. And then your TOEFL exam will be from July 27 to August 3. And guys, take note of this change. Your evaluation exam discussion video will be released on August 16. Kindly take note, guys. Ayun naman, so I hope that you have learned a lot today about phase equilibria. And the next time we will meet, we will learn about electrochemical equilibria, chemical kinetics, and special topics. So guys, again, if you have any questions at all, please don't hesitate to ask me. Okay? I'll try my best to answer you as soon as possible. Okay? Bye guys, and thank you. See ya.